Hello students, after understanding the diversity concept and the wireless communication channel characteristics, today we will start understanding the Rake receiver, which is the very popular means of combining the and getting the diversity gain. It is basically the main mean of receiving the diversity gain or achieving the diversity gain in a spread spectrum communication receiver, and we will see how the receiver architecture looks like, and also we will learn the performance analysis of this receiver architecture. So, remember one thing, the whatever the receiver architecture you have already gone through for direct sequence spread spectrum and frequency hopping spread spectrum communication system in the first few modules. They are true, but excluding the effect of the diversity gain. If you wish to incorporate the diversity gain into the receiver performance, then you need a special kind of the receiver architecture, which we today is a discussion point of ours, and today we will, hence this architecture is called the Rake receiver, and today we will discuss on that. As I have already mentioned, Rake receiver in a fading environment, especially in the wireless fading environment, it is a means of to achieve the benefits of the diversity combining, and that combining is possible in the architecture which we call a Rake receiver. And Rake receiver is a very standard type of direct sequence systems which are these days used in the mobile communication network. The way Rake receiver works is like this. He provides a path diversity by coherently combining the resolvable multipath components, and after properly processing them inside the receiver over a frequency selective channel. And so, what he does, we understood in the wireless communication architecture, wireless channel. When we saw the channel and understood the channel characteristics, we saw that from transmitter to receiver, the rays does not only arrive over the line of sight path, it gets scattered, it gets reflected and scattered over the multiple scattering environment, and it reaches to the receiver over the multiple paths. So, Rake receiver is supposed to have the capacity to encash this path diversity if the same signal is coming over the multiple paths, and if you can resolve them inside the receiver, capture each path signal independently, and hence after proper processing of those path signals, if you can combine them synchronously, if you can do that, then actually you will get the gain of the diversity gain, actually we call it, we will get the gain, a huge SNR gain over the in the receiver. And this happens over the frequency selective fading, it can give a huge gain, and Rake receiver architecture is supposed to capable of doing this. We will see how. And let us consider a situation where the frequency selective fading is going on in the channel, and but the fading is slow. That means the time variation of the coefficients of the channel is relatively very slow, and relatively it is slow relative to the signaling interval. So, whatever the coefficients, frequency selective path coefficients you are estimating, we consider that that is not varying over very fast with respect to the signaling interval. And to harness the energy to over all the paths, for each of the for all the multipath component paths, a receiver should decide what he should decide that which signal was transmitted. Suppose I have an M array signal, and if it is an QPSK signal, you will have at least 2 branches of it. If it is an M array signal, you will have M different signals corresponding to the transmitted signal. So, we will have, depending upon the Bessel's functions you are using, you will have multiple such signals, combination of the such signals constituting your signal. If it is a 16 QAM signal, so you will have the numbers of the S values. So, consider an array of the signals, M array signal, where the number of the signals constituting this array varies from S1t to SMT. Okay. The task of the receiver is to find out that which of these signals have been transmitted, also resolve the corresponding multipath components corresponding to this transmission. So, that is the task that we are going to discuss. And for that we have chosen an environment where your frequency selective slow fading environment it is, and hence the estimated channel coefficients and the channel phases are not expected to change very frequently over time relative to the signal duration. So, the receiver's task is what? Receiver task is to select among all the m number of the baseband signals which one is transmitted. It selects actually one of those capital M set S1 to Sm, and it actually or it can compute also the complex envelopes of it. But fundamental point is that corresponding to each and every signal component, he actually enables, he combines the effect of all the multiple paths in the Rake receiver. So, you see the received signal at the Rake receiver is something like that. Yeah, this is your transmitted signal SKT minus tau I, where k can vary from 1 to capital M, because I understand that the signal is drawn from capital M array signaling. Small t is actually this t will be varying factor, and he will have a variation up to t plus t d, where this t is the duration of the transmitted signal and t d is the multipath delay spread. Maximum can happen over the given channel, and tau I is the delay of each and every multipath. Corresponding to that multipath delay, we are having a channel coefficient C I associated with it. It is a complex value channel, and remember that I can vary over I to capital L. We understand that capital L is a number of the multipath components present in a environment. So, the received signal at the output of the Rake receiver will be the combination of all those multipath signals for a typical signal transmitted from the set of the baseband signals. Remember actually which of those M signals were transmitted. In order to decide on that, Rake receiver should process similarly by varying k over 1 to all number of the 1 to a capital M, I mean all available number of the signal set. So, he independently and separately processes all those M set signals, and then run the decision over all of them, and then decide which of the signals have been transmitted. Please remember this equation 1.1, we will refer this equation again and again in the corresponding slides. And let us sketch actually and understand what is going on in the environment and how the receiver is receiving the multipath signals. This is the figure 1 is an idealized sketch of the whole situation. Remember the output of the baseband match filter. If the filter is matching with the 3 components of the multipaths, so output of the baseband match filter for all those 3 paths will look like this. Okay, we have received, this is the power level received. So, I have reduced the power level considering the fact that more the delay you are tracing, the power is getting slowly reduced, because it seems that the more delay means the ray has traversed more path, and hence the possibility of absorption of the power over that path will be high. So, you are receiving a very low amount compared to the previous one. And then if the match filter is matched with the individual 3 multipaths say, then the output of this baseband match filter will look like this over the delay axis. But remember one thing, if my signal is having a bandwidth of capital W, then the duration of the match filter that responses to that signal W, the duration of the match filter should be 1 by W. And hence the multipath components that produces the distinguishable match filter output pulses, we call them the resolvable multipaths. So, multipaths may be actually also in between, but the based on the zooming capacity of the receiver, I mean the bandwidth of the receiver circuitry, and it is dependent upon that actually the how good resolvable, how resolvability is possible, how much, to what extent the resolvability of the receiver works, and hence how many number of the multipaths you can resolve at the output of the baseband match filter. And those multipath components are called the resolvable multipath components. So, according to this figure, we have 3 resolvable components. Remember one thing, we have considered that T s is the sampling, the duration of the symbol, and tau d is our delay, maximum delay that we will consider for the analysis. Another important part to notice here is if the delay, this total delay is less than the symbol duration. So, this multipath spreading or this delay spread, and hence the dispersion of the signal won't contribute to any intersymbol interference, because it won't overlap with the next symbol coming up at the moment of 2Ts. But if it is not the situation, if the multipath components are having significant power and you are continuously watching them over the delay axes and all other resolvable multipaths, it may happen in such situation, in certain situation, that they are having significant amount of intersymbol interference because of the dispersion, time dispersion, or the delay dispersion over the delay axis of the signal. It also happens to be creating the intersymbol interference if the data rate is very high, and hence your time duration between the symbol duration will be very less, and if the multipaths are having the delay spread of the channel is having very high, then in that situation you will be ending up with very high amount of intersymbol interference. So, they are resolvable, the 3 paths in our consideration will be resolvable, and if their relative delays are greater than 1 by w in this situation, we can resolve them. So, we understand actually the necessary condition that for at least 2 multipaths you can resolve. The condition is such that the duration 1 by w, the duration 1 by w should be less than the delay spread of the tau d. So, in that situation only there is a chance that at least 2 multipath you will be able to see. And we have already understood and read that the coherence bandwidth of the channel, the BC, it is the coherence bandwidth of the channel. So, the coherence bandwidth of the channel is having some relation with the maximum delay spread. So, this coherence bandwidth can be given by the, basically it is the RMS having a relation with RMS delay spread. Roughly it can be approximated with the TD, the maximum delay spread that we are having. So, BC is equal to 1 by TD. It follows from here that if I now wish to, if I have a signal bandwidth which is more than the coherence bandwidth of the signal, or more than the coherence bandwidth of this, and which implies that the frequency selective fading and the resolvable multipath components both are actually associated with a very wide band channel, wide band signals, wide band signals. So, actually we understand that the coherence bandwidth, in order to have a coherence bandwidth, actually if it is in a frequency selective situation, then the signal bandwidth will be definitely more than the coherence bandwidth situation, and the number of the resolvable multipath components and all the phenomena is getting associated with this frequency selective fading as well as with the wide bandwidth signals. So, what we will expect in such situation is, we can expect at most the number of the resolvable multipath or the components should be that TD into 1 by capital T, because W is equal to your 1 by capital W is 1 by W is equal to your the time of T is equal to 1 by W. So, this is the time, this is actually the period by means of which the sampling is going on inside the Rake receiver, or the match filter bandwidth, I should say. The match filter bandwidth is working upon, and hence it is basically, if I substitute it, this whole equation is basically your delay divided by the capital T. So, number of the multipass that you are getting plus 1, because the first one is obviously will be achieving, from where actually your matching should start or the delay computation should start. And so, T d by T, if you take the largest integer part of this expression plus 1, this is the number of the resolvable multipath components that you can expect. So, see, the number of the resolvable multipath components highly depends on the bandwidth of your match filter. As we have seen there, that the intersymbol interference, as I have already informed, the intersymbol interference to come into picture, either the data rate needs to be high or the T d by 1 by W. If this whole part is less than the symbol duration, you won't get any intersymbol interference. Otherwise, unless you will get any one where is changing, or if your data rate is increasing. And for the next part of the analysis, let us assume that this capital M possible signal sets, they are all orthogonal to each other. And also let us think that we are getting we are receiving the data symbols which are all independent to each other, and so that in the receiver, the maximum likelihood receiver, it makes the decision about which symbol has been received. That decision is going on symbol by symbol basis. So, this receiver uses now a separate baseband match filter for each and every symbols that they will be dealing with, and every symbol will have a possible desired number of the multipaths components associated with its processing. So, if we start with a signal called SKT for the kth symbol, and we understand that this is a symbol waveform, and for the kth symbol, that k can vary from 1 to capital M, then the kth match filter output will be that equation 1.1. We started with it is saying it is a signal. Now, it will also hold good for a symbol, that is the meaning, where actually you have to consider that capital T is not the signal duration. Now, this is the symbol duration T s. So, now in the each match filter output, now you have to sample. The sampling should be done at the gap of the symbol duration plus T d. It is not T plus T d, it should be T s plus T d if you are taking the sample. And the decision variable, it can be given well established result, it is. So, it can be given by the taking the real part of this equation 1.4. Remember what we have done here, the CI is the summation is going on over the all number of the multipaths. You have taken the complex valued coefficients of the channel from each and every path, and this is the signal you have received, the match filter associated with it, and you are integrating it over the duration of T s plus T d, because that is the symbol, that is the sampling duration that over which your integration is going on, that the sample duration over which you are going to get the samples and take the real part of it and take the decision whether the symbol transmitted is 0 or 1. And when we am talking about this RT is the received signal, this signal is spread signal with the noise, as and it is after down conversion only, you have taken the down converted signal only, it is fed here. So, this is a whole baseband decision variable is running on the pure baseband. The receiver implementation, now if I try to do based on this, it seems to me that it requires a separate transversal filter for each and every symbol or the delay line, and then a match filter is required each and every associated with each and every symbol. Or alternatively, I can do something else, a single transversal filter will be there and m number of the match filters I will deploy, and then the and we understand that this SK, it doesn't exist beyond the duration of this symbol interval 0 to T s. If I try to do that, then the alternative figure would look like something like this. I will come back here, but prior going there, we would like to revisit the decision variable, how the change is happening. If I change that structure like this, that I will have a single transversal filter with m number of the match filter, and then how this will change. this will now change like this, as if that I am having the duration of 0 to t s, and this r tau is now having tau plus tau y. Tau y will be given by the number of the, it is a delay associated with each and every multipath, but it has a maximum value which will be defined as the tau m, which is the maximum delay. So, tau can vary from tau plus tau m, it seems, and then sk star is the match filter function, and then the match filter will be running over the tau. And for frequency selective fading and the resolvable multipath components, this simplifying assumption is that each delay is an integer multiple of this 1 by w, that is the match filter duration and filtering duration. So, accordingly this L increased, L is increased to equal to the maximum number of the resolvable components only in our discussion. And if I try to go ahead by this equation 1.5 finally, and we may see that some of the components coming from the channel, I mean the Ci values may be equal to 0 also, and the decision variable then finally can be written like this, where this one will be, this will be not tau, this will be small r. And so, finally, this guy will be replaced by this r out r tau plus I minus 1 by w. This I minus 1 by w is nothing, but the expression that we are getting for the expression of the tau m. So, I is varying up to capital L, that is why if you substitute L minus 1 by w, 1 by w is the gap of the arrival of the multiple paths, as we have understood. So, this is the match to that, and then you are ending up with the maximum L minus 1 by w is given by the maximum delay split tau m. So, we have just replaced this tau I by this expression, where I is varying slowly from 1 to capital L. And with this, we are now ready to go with the figure. Remember one thing that we have seen in the earlier expression. So, let us revisit the expression once more, how this is the final expression we are ending up with. Remember a situation that we are having the received signal which should have the delayed up to the tau m. So, we are having the final signal r t, this is the first path came, and then the delayed paths are actually having a gap of, these are the multiple paths arriving at a gap of 1 by w, and the last one that you are going to receive is t plus tau m. And this is the structure of the transversal filter, and at the output of the each tap. So, output of the final tap of the filter, you are getting the signal r t, and others are giving the delayed pulse, multiple pulses. So, this if I draw it like this. So, this was there with respect to tau equal to 0, if this is my tau axis. So, I received the first path, say tau is equal to 0 at tau at t, then the second one came, third came, fourth came, like that. The r t plus tau m came at last. So, when I saw the filter structure, I will be here, and these are all the before pulses that came earlier. So, all the pulses have been shifted like this, and you are ending up the last one, the last multipath is entering here. And all the filter taps, the output of the filter taps are accordingly adjusted. These are the CIs that you are adjusting, and according to the transversal architecture, the transversal filter architecture, we have filter architecture, we have added it, because this is the addition happening. There the filter will be happening, multiplying with it, and then it is adding up. So, that addition is done here. And now, the output of these filters are they are fed into the match filter, m number of the match filters we are having, and the real part of all those finally after having the match filtered output, this is multiplied with the match filter, and then after the match filtered output, the real part of that you are taken, and that operation is going on for each and every k symbol, and so you are having capital M number of the symbols, and corresponding to the each and every path you are getting either u1 to um. So, if this is the way that we have this called the whole architecture is according to the last equation that we have developed, and then the decision variable will work saying the taking the actually the decision of a symbol by symbol basis. So, remember here one thing, that how will you know that the values of the CIs, I mean the channel component values, how will you compute is a very big question in the whole Rake receiver architecture. So, what I mean is that the channel parameters you need to be known, both the delays as well as the CIs. Otherwise, you won't be able to actually design the filter coefficients and the filter can set the filter parameters. And this estimation is done by applying the each tap output of the filter to the m parallel match filters after a one symbol delay, and the previous symbol decision is used to select any one match filter output for each of these tap output. So, now that capital L matched filter outputs are the low pass filtered, and then it is providing us the estimate of the channel parameters, and these estimates we should update at the rate of the fade at a rate which should not exceed the fade rate. So, it should be actually at par the rate of the fading, at the rate of the slow or fast fading I mean. So, that estimation should go according to the rate at which the channel is changing. So, an alternative configuration of this previous one we can have in the figure 2, where with the separate transversal filters we can also apply for the decision variable and has a corresponding match filter for each and every symbol in the front end, and then can have the parallel fingers, we call the Rake fingers at the output of the match filter. And remember, actually for those filters, let us see first the structure, the alternate structure of the previous transversal filter. What we did is, we have received the signal and we have associated a match filter to that signal. Output of the match filter is sampled and the sampled output is fed to the fingers. Remember, the structure is such that the match filter output, if they are matched to the structure, remember the first figure, the match filter outputs will provide like this, and so these fingers are such that the fingers are coinciding, picking up actually they are picking up the corresponding multipaths, they are having the typical delays associated with it. Inside the finger we have the correlators like this. Inside one finger we have a correlator. So, figures basically actually the match filter output, the sampled output is entering into a finger and it is delayed by a specific amount. That delay will be the delay of the corresponding multipaths, and then you have a channel estimator running with it. So, you need to multiply the CI with the delayed path to undo the effect of the channel with this multipath component, and then you take the real part of it. So, that is the motivation. And remember how many number of the fingers, the number of the fingers are expected to be equal to the number of the multipaths, resolvable multipaths that we are interested in. But in such a situation, if the channel varies, the number of the resolvable multipaths also will be varying. So, how will you keep on changing the finger size if you deploy the Rake receiver finger fixed size of the how can you vary the number of the fingers in a practical circuit is a very big question. What we do is that we try to define here the significant number of the multipaths. Multipaths may be enormous in number, but significant multipaths means who are having a significant amount of the power. We actually are interested in all them, we shift all that and we actually coherently try to process them and adapt. So, if I independently and coherently time shift all that and undo the effect of the channel for each and everybody and then add them up here. So, then finally, I can actually take a decision of the transmitted symbol based on the output seen here, definitely the real part of the UK we are interested in. And remember that in practical circuit the fingers are not variable, fingers are always fixed. So, we try to keep the finger fixed, and whatever the multipass we can capture based on the maximum one. So, LS will be all if the maximum number of the fingers present in a structure Rake receiver architecture is L. So, L will be always greater than the or greater or equal to LS, that is the concept for the architecture of these fingers. And you may actually definitely process this section or these fingers in the digital domain, because the match filter output you are getting in as a sample. So, it is already sampled, and so it is a task of the finger to get aligned with each and every multiple path that you are receiving corresponding to one symbol. Now, two more important part, the delay of this significant multipath component, they needs to be estimated, right. So, they can be estimated by using some envelope detectors and some threshold devices also. And suppose this T denotes the time required to estimate a relative delay of a multipath component, and let V is denoting the relative radial velocity of the receiver relative to the transmitter. So, this receiver velocity and then V into T e by C, this is the rate of change of the delay, it should be, where C is the speed of the light. So, this is the rate at which the electromagnetic, it is a rate at which the delay is expected to change, and your basically that actually if this change occurs, and within that your estimation procedure, within the estimation procedure this is the change has happened at this rate, then your estimation process itself is not going to work finally. So, how actually it should be working? What is the basic relation between this estimated time T e and the relative velocity and the bandwidth at which with which the selection bandwidth of the match filter, how does they work together? It is like this. So, if we know the V, it is interpreted as the maximum speed of the mobile in a mobile communication network, then the estimated time should be always less than equal to the C by V into W. So, this W is a parameter of your own choice. V may be actually freely moving by the, it is a velocity of the mobile with which it is moving, but you can actually do the computation with the maximum speed possible in a mobile environment, and you can compute the maximum limit of this estimation T e for the multipath delay estimation inside the receiver. And that is the very golden rule that you have to follow to update the delay estimation inside the Rake receiver. And now, the last one is suppose that SKT, the symbol that we have transmitted, the direct sequence signal, that has a chip duration T c, which is actually equal to 1 by W. And if then the processing gain is really very large, the spreading sequence has a very small autocorrelation when the relative delay is T c. That if the relative delay is itself T c or it is more, then the autocorrelation will be actually very small, and hence in this situation it can be easily written that this expression or say this expression, left side expression of the symbol, with every delay, if I shift and then you multiply both of them over 0 to T s, the symbol duration, then it should be always less than equal to the actual signal squared it up, for I definitely greater than equal to 2. So, these are the two important part that we will carry forward in the next module, when we will do the performance analysis of this Rake receiver further, in order to find out what is the error probability for a typical modulation scheme coming from the Rake receiver. But remember, there you have to keep in the mind that whatever the estimation process parallelly running inside the Rake receiver, it is following this rule, and also we will consider that the processing gain is really very high, such that this equation holds good.